Okay, hello and welcome. This is actually the first lecture for SFU Math 232, Linear Algebra. So we're going to start with Chapter 2 because many of you are already familiar with linear equations and solving systems of linear equations. So I think it's a nice place to start this course. We can do some things that you are familiar with while also introducing maybe a little bit of vocabulary. And then once we finish chapter 2, we'll go back and do chapter 1 where we introduce more of the abstract notation and such that we'll be using throughout the course. So that's my plan. My name is Brenda Davison, and we're going to start here with section 2.1, Introduction to Systems of Linear Equations. So there's a very old linear algebra problem here. 3 classes of corn, and then if you take 3 bundles of the first class and 2 bundles of the second class and 1 bundle of the third, you get 39 measures. And if you take 2 of the first, 3 of the second, and 1 of the third, you get 34 measures. And 1 of the first, 2 of the second, and 3 of the third to get 26 measures. And then it asks how many measures of grain are contained in 1 bundle of each class. So this is the type of systems of linear equations we're going to be seeing how to solve. And this is an example from really a long time ago, China, 100 BC roughly. Okay, so let's pay particular attention in this introduction, this sort of first lecture, to the words we're going to use, the symbols we're going to use, so that we can understand one another well. Okay, so I'm going to define the words that I use, or I'll at least indicate that they'll be defined clearly later. So we'll start here with the definition of a linear equation. So the first thing to notice is the word linear actually contains this thing here, a line. Okay, so that's how we'll be thinking of it, at least in 2 dimensions. Okay, so a linear equation in n variables. So these x1, x2, xn are variables. And if we have a linear equation, we can write it this way. We write it with a number, that's a constant, that's some number times the first variable plus some other number times the second variable plus, etc., till we get them all. And then we have another number over here by itself. Okay, and we're not going to have a linear equation unless not all of the AIs are 0. We have a special case that will actually become very important. So there's 2 possibilities here for this number on the right-hand side of my equation. This b could be equal to 0, or it could be not equal to 0. That covers all the cases. So if it is equal to 0, we call it homogeneous. So that's this one here. That is homogeneous right there. That was a star until my computer screen there moved. That is homogeneous. And then if it's not 0, we call it non-homogeneous. So that's actually going to become important, that distinction, whether there's a 0 sitting there or a not a 0. So let's just get some examples of linear equations and perhaps not linear equations so we can see the distinction. So here's a linear equation. 2x1 plus 3x2 equals 0. That's a linear equation. We have x1 and x2 as the variables. We have 2 and 3 as the constants, and b here is equal to 0. So in fact, this is a homogeneous linear equation. You'll notice that the power on the variables is 1. So like we don't normally write this here, but we could, for example, put x1 to the 1. So basically what we're looking for is equations where the power on every variable is 1. Okay, so that's a linear equation. Here's another linear equation. Okay, that first part is the same, but this is a non-homogeneous linear equation because this thing here is -6, it's not 0. Okay, so this is a linear equation in 2 variables, and this is also a linear equation in 2 variables. Let's take another linear equation. Here's another linear equation. That is a homogeneous linear equation, and it is a linear equation in 4 variables. Okay, we're going to typically use x1, x2, x3, x4 like that for the variables because we can simply expand up to as many as we like very easily. Sometimes in the past you have seen these ones written this way, 2x plus 3y equals 0. So, and then we would represent that typically with the x-axis and the y-axis like that. There's exactly the same is if we were to do 2x1 plus 3x2 equals to 0, and then call this thing here x1 and call this thing here x2. Okay, it's just that when we have two variables, we often say x and y. And in fact, when we have three variables, sometimes we'll say x, y, and z. Sometimes we'll say x1, x2. Sometimes we'll say x1, x2, x3. But certainly once we get beyond 3, we tend to just label them 1, 2, 3, 4, etc. Okay, let's take just for contrast a couple of equations that are not linear. So let's not confuse ourselves. So these ones coming in black are not linear. So here's a nonlinear equation. Okay, all right, and we know it's not linear because of that thing right there. This is a quadratic. Okay, so it's not linear. So the powers on all of the variables have to be equal to 1. Here's another nonlinear equation. Square root of x1 minus x2 equals 3. That is also nonlinear, and that is because the power here is not 1. This is x1 to the 1/2. So that's also not linear. Okay, the next thing we're going to ask ourselves is what does a linear equation look like geometrically? So what do they look like? Again, let me point to this sort of thing here, at least in the two-dimensional thing. We do have a clue sitting right there. So let's first make sure we understand this notation here. So R here is equal to the set of all real numbers. So that's our number line. Okay, so there's, if I was going to try to represent that like that, R, I would represent it like that. That's the number line. R2 is, we think of that as R by R, if you will, and that is our plane. So this is our Cartesian plane. Let's try that here, Cartesian plane. Okay, perhaps you can think of it this way. You have one real number line that way, often labeled X, and then one real number line this way, orthogonal to it, often labeled Y. And R2 is this the whole plane there. Okay, the two-dimensional plane, right? You can get that clue there. It's a two-dimensional plane. And then we can have R3, and we typically, drawing on two-dimensional paper, we'll typically draw that this way, X, Y, and Z, and R3 is the whole of space. So R3 is our typical space. Now, if we have a linear equation in R, let me just erase this so I can unwrite this. Linear equation in R, that means we have one variable. Okay, so I'm first going to talk about here in R. Okay, we would have an equation that looked like this. 3x1 equals 2. I mean, that could also be written the same way, like this. x1 equals 2/3. Okay, and what is that? That is a dot. That is a point. I mean, we would be up here on our number line, and we would say, there it is, 2/3. It's a point. Okay, and then in R2, we would have two variables. We would write it like this, perhaps 3x1 plus 4x2 equals 6, like that. And then we would mean all pairs, x1 and x2, which make this equation true. And that would be a line, some line like that. So it would be all points that make that satisfy that line. So in R2, a linear equation is a line. In R, a linear equation is a point. And then in R3, we would have an equation that looks like, well, since I've labeled these x, y, and z, let me write the equation like this: 2x plus 3y plus 4z equals 10. And then that would be some type of a plane. So that would be some type of a plane sitting here in R3. Okay, so we have a sense of what these things look like geometrically. And I'm going to put a lot of emphasis in this course on the geometric interpretation because I think we're going to get quite abstract at times, and I think it's very nice to always move back and say, okay, what does this look like in at least what does it look like in 2 or 3 dimensions where I can visualize things nicely, and then maybe expand up from that perception of what's going on. Okay, so we've defined what is a linear equation. Now what we're going to do is define a system of linear equations. This is not at all difficult. We just take a finite set of linear equations. That's what we call a system. We'll sometimes call it a system of linear equations, or sometimes we'll just call it a linear system. The variables are still called the unknowns. So here is a general case here of examples, and that is we've got several equations here. In fact, the way it's listed here, we've got m equations. So this would be equation 1, equation 2, etc. And this is equation m. So there's m equations. Oh, I will also, let me write that out fully, and then let you in on all my abbreviations. So that's m equations, and I'll often write equations like this, shorthand, like that. Okay, each one of these equations has m unknowns. So these are the things that are not known, the variables, x1, x2, xn, etc. So these are n unknowns. Okay, let's take a very simple linear system. Here's a linear system, 2x1 plus 3x2 equals 5, and 4x1 minus 2x2 equals 6. Okay, here we have two equations, 1 and 2, and we have two unknowns. We have two unknowns, x1 and x2, two unknowns. Okay, two equations, two unknowns. It's a system of linear equations because it's not just one. We've got two of them, and we have basically three possibilities for what the solution set of this could look like. Okay, what is this word solution set? Let's be careful that we know what that means before we discuss what the possible solution sets of this of a linear system of two equations and two unknowns looks like. So what do I mean by solution set? A solution a solution to a linear system is a sequence of numbers that, when you substitute in for the unknowns, satisfy all of the equations. So we can represent each solution as a point or a vector in n space. So this vocabulary here, just hang tough on that. We're gonna retreat back to lectures in chapter 1, and we'll clarify some of this jargon for you then. But what basically we're saying is a solution is are the values for the unknowns that make all of the equations true. And we call the set of all of those solutions the solution set. Okay, so we've got two equations, two unknowns. This is, for most of you, not new ground. So what can happen? We've got two lines, basically. What can happen? So let's just draw the situation out here. We got x here and y, and we could imagine that line 1 would look like that, and then line 2 would look like that. Okay, each one of those lines, let us just say this is line 1 and line 2, and then I drew here line 1 and I drew line 2 here. Okay, line 1 is all of the points that satisfy equation 1. Line 2 is all of the points that satisfy equation 2. And in this drawing, there is exactly one point that satisfies both of them. That is this point here, the intersection point. So here, the plausible solution sets, well, here's one possibility. The solution set contains 1 point. Okay, that's possibility 1. There are other possibilities. Let's take a look at another possibility. I have 2 lines, and the one line looks like that, and the other line looks like that. These are parallel in my drawing. So this perhaps could be line representing equation 1, and here's the line representing equation 2, and they are parallel. So these lines are parallel. Okay, now there are, so on line 1, those are all the values that satisfy equation 1, and on line 2 are all the values that satisfy of x and y that satisfy equation 2, and there are no values of x and y that satisfy both equations. So the solution set is empty. Okay, that's the second possibility. There is one other possibility. That possibility is that the 2 lines are one on top of the other. So let's just draw that one here. So I take here x and y, and then I have one of my lines. There it is. There's line 1. And then it turns out that line 2 is in fact the same line. So it goes directly on top like that, line 2. So line 1 and line 2 are completely coincident. And so that means then the solution set is all of the points on those 2 lines. So the solution set contains infinitely many points. Okay, those are the only 3 possibilities. Okay, what happens if we have 2 equations and 3 unknowns? Okay, so this one's a little bit more complicated. So each one of these is a plane. Each one of these things is a plane, so that we've got 2 of them. We've got 2 equations. Each one is a plane. Okay, so what are our possibilities? Well, they could be the same plane. And if they're the same plane, then we have an infinite number of solutions. So if they are the same plane, so notice I'm here, 2 equations, 3 unknowns. Same plane, that's going to be an infinite number of solutions. Okay. If they're parallel planes, so I would have a situation where I would have an axis system here, and I would have, say, one plane sitting here like this, like that, and then here this is my x and my y and my z. So I have one plane sitting here like that, and then I have another plane in behind, oriented also vertically. So I've got 2 vertical planes, one behind the other, and they do not intersect. So this is another possibility. These are the parallel planes. And then that's going to be no solutions. So there'll be no set of 3 numbers like this, a solution set. There'll be no, there will not exist specific numbers x, y, and z that will solve equation 1 and equation 2 if the 2 planes are parallel. Okay, and then there's a third possibility, that is that the planes intersect. So we could imagine, for example, we had 2 planes, and one of them was like this. In fact, let's call this like the XZ plane. And then we had another plane, which was like this. Let me draw this one in a different color. We had another plane that looked coming like this. This oriented at, in this case, I try to draw it roughly oriented at 90 degrees, and then the 2 of them would intersect at a line. That is a possibility. That is the third possibility. So they would intersect here at a line. That's where the black plane, you could imagine that as basically the XZ uh, a plane, and then imagine the red plane as being the YZ plane, and you see them intersecting in the Z axis. Okay, so that's the other possibility, intersecting plane. And that is solution set is a line. Okay, all right, and I've got thankfully we have computers that we can draw things nicely with, and so here is the general case in 3 dimensions when we have 3 equations and 3 unknowns, and we've got some possibilities here. We've got all 3 planes are parallel. There's no solutions. We've got 2 of the planes are parallel, and then the other plane intersects them both, but all 3 of them do not intersect. Still no solutions. The 3 planes have mutual intersections, but they don't. None of them intersect in the same place. You sort of got this distance between them all. That's also a no solutions. We have all 3 planes are on top of one another. Then we have infinitely many solutions, and then we have a situation here where through the 3 planes are intersecting in a line, that line being right here. So we have infinitely many solutions. That is, the intersection is a line. And then we have the thing that this is much like the origin. You could think of that as well. Like when you have 3 planes, imagine the plane here, and then the plane here, and then the plane here, and they are all intersecting like that at the origin. That's this case here. You've got 3 planes, and they are intersecting in one point. Then you have a couple of other possibilities. The 2 planes are on top of one another, and the third one is parallel. No solutions. And then we have 2 coincident planes and 1 plane intersecting the 2 of those, and then you get a line for an intersection. So we've basically got a situation where we've got no solutions, infinite many solutions, and 1 solution, which is exactly like the 2 by 2 case, in fact. Okay, and we'll capture that idea in a theorem. Every linear system has either 0 solutions, 1 solution, or infinitely many. There's no possibility. You don't end up with a situation where you've got 10 solutions. That does not happen. You either get 0, 1, or infinitely many. Okay, if there is at least 1, then we call the system consistent. Otherwise, we call it inconsistent. Okay, now here's going to come a big idea. What can you do to your equations such that the solution set is not changed? So I'm gonna go through this in quite a bit of detail because we want to have the idea that we can do some things to a system of equations and the solution set remains unchanged. It's a big idea here. This word here, scalar, let us just think right now as that as a number. It is a number, not a vector. Again, some of this vector scalar thing is going to become completely clear when we do the lecture for chapter 1. But right now here I want to start with these linear equations because they are more familiar. Okay, so let us take a look at a 2 by 2 system of a linear system. Okay, I'm gonna label the equations, and we're gonna take a look at doing these operations here and observing that the solution set, the numbers that solve these equations, do not change when I do A, B, or C up there. Okay, so here's my example. I'm going to have equation 1, 2x1 minus x2 is equal to 4. And then my second equation, minus 2x1 plus 2x2 is equal to 6. Okay, first of all, we know how to do this. Let's just solve this thing, and so we know what the answer is. Okay, so I'm going to add them together. So now I'm just going to add the 2 equations. Add 2 equations together. Okay, this is something you've learned how to do in high school. So I'm going to add them together. I'm going to end up with x2 equals 10. And then I'm going to do what? I'm going to substitute that into the first equation. So I'm to take, okay, I'm going to write that like this, into 1. So that's going to be 2 times x1 minus x2, which I now know is 10. And that's going to be 4. So I end up with the fact that x1 is 7. So I have a solution to this thing. It's 7, 10. x1, x2. That's my solution set. I know this. Okay, now what I want to do is we're going to notice a few things. We have a system of 2 linear equations. We found the solution set. Now what we're going to do is consider this. Consider this system. Minus 2x1 plus 2x2 equals 6, and 2x1 minus x2 equals 4. Okay, what have I done? I just wrote them in a different order, right? Like I could either relabel, or I could just point you to notice that this is now, like, the first one is now what was previously 2. So I've just written them down in a different order. It has the same solution. I mean, clearly it has the same solution. If you want, you can go ahead and solve this one again, but I think it's pretty clear that this has the same solution set. That's the same solution set. That is this solution right here. Okay, so what is this? This is an example of B. Okay. What do I mean by B? This guy, B. It's an example of B. Interchange 2 equations. The solution does not change. Okay, that's the first one to be aware of. Okay, let's take a look at the next thing. Let us consider this guy here. Equation 1 is going to be written like this: 4x1 minus 2x2 equals 8. And equation 2 will look like this: minus 2x1 plus 2x2 equals 6. Okay, you can see that equation 2 here is the same as equation 2 here. Equation 1 is not the same, but you can notice that equation 1 is here. This equation 1 is 2 times this equation 1. Like, I just multiplied both sides by 2. Now let's solve this. Let's solve this system here. I'm going to do that by, so I'm going to take these 2 equations here. I'm going to solve them. I'm going to do that. I'm going to add the 2 equations together. So I'm going to add 2 equations together, and I'm going to get what? 2x1 equals 14, x1 equals 7. And then now that I know that x1 is 7, I will go minus 2 times 7 plus 2 times x2 is 6. 2x2 is 20. X2 is 10. And right, I have the same answer. So the fact that I took that first equation, multiplied it by 2, it didn't change anything. The solution set is exactly the same. That is A. Example of A. Okay, that's A. Multiply one of the equations by a non-zero scalar, a number. Just multiply, and in this case, the non-zero scalar was 2. All right, let's now try again here. Let's consider this. Consider this system. How about this? 2x1 minus x2 equals 4. So that's equation 1 as before. How about this equation? Equation 2. Here's equation 2. 4x1 minus x2 is equal to 18. Let's see. 4x1 minus x2 equals to 18. How am I? Okay, what do I want you to see before? Maybe we should just find the solution to this system of equations. Let's find that. Let's take 2 minus 1. I'm going to take equation 2 and I'm going to subtract equation 1. And what does that get me? 2 minus 1 gets me 2x1 is equal to 14, or x1 is equal to 7. And then I can substitute that in. 2 times 7 minus x2 equals 4. And I get that x2 is equal to 10. Okay, it has the same solution set like the other ones. Now let's take a closer look at this equation right here. What is that? Well, what did I do to get that? I took 3 times equation 1. So I went like this. I took 3 times this. Okay, and then I added it to this. And when I multiply by 3, I call multiply by 3 on both sides. Actually, I want to do it this way. I'm multiplying by 3, the whole thing. So I took 3 times the first equation, and then I added it to the second equation. So I've got 6x1 minus 2x1, and I get 4x1, and then I have minus 3x2 plus 2x2, then I get 12 plus 6, which is 18. Okay, that's my equation 2. So I took, of the original equations that I had, I took 3 times the first one and I added the second one. This is an example of C. That's an example of C. Add a multiple of one equation to another. So it's by no means a proof, but I want you to be very clear that when I have a system of equations and I do A, B, or C here, I get what looks like another system of equations, but it has the same solution set. That's a big idea. We're going to use that all of the time. We can adjust using those 3 things without changing the solution set. Okay, our next thing here is to get a bit of excuse me, to get a bit of shorthand notation. Okay, and then we're going to find, actually, we're going to use shorthand notation here to represent these systems of linear equations using matrices. And then we're going to find actually that we can do a bunch of interesting things on the matrices themselves, and actually they become much more abstract than just representing linear equations. Okay, so basically right here I'm saying this is pretty cumbersome. This is cumbersome. Okay, so you need some sort of shorthand notation. So what we do is we write we sort of in a sense say, you know what, we already kind of know that this is already x1, this is already x2, we know this, it's going to be xn and all of these, and we know that there's an equal sign, right, on all of them. So all we really need to do is capture the coefficients, the A11, A12, etc. And then also on the right hand side, we need to capture the B1, B2. So we write it like this, and I'm going to, for the most part, be adding, and when I write it out by hand, having a line there to say these numbers here, we're putting in here are the coefficients of the linear equations, and then we've got that right hand side set of numbers, B1, B2, Bn. So we take our system of linear equations and we capture all of the information in what we call here an augmented matrix. It's an augmented matrix because these values are here as well. Okay, so that's that word there, augmented matrix. Okay, so let us just take a couple of examples of this so we can see how to do this. Okay, so we've got here, we've got 2 equations and we've got 4 unknowns. We want to write out what the augmented matrix is. We simply list the coefficients in the first line, in the first row here, like that. So I've listed the coefficients of the first equation in the first row, and then I list the coefficients of the second equation in the second row. Okay, there it is. So that is the augmented matrix of the above system of linear equations. Let's do another example. x1 plus x2 equals 6. Here's a system of linear equations. This one is having two equations and two unknowns. Okay, so rather than write it like that, I am simply going to rewrite it with its augmented matrix. So that is going to look like this. The coefficient on x1 in the first equation, the coefficient on x2 in the first equation, and the b value on the first equation. The coefficient on x1 in the second equation, the coefficient on x2 in the second equation, and b2. There it is. We've got now a second system. So when we are talking about a system of linear equations, this representation means exactly the same thing as this representation. Now we can go the other way. Imagine somebody gives you an augmented matrix. Like that. And then you're saying to yourself, let me just write out the system of equations. Then I would write it like this. 2x1 plus 3x2 equals minus 3, and 4x1 plus 5x2 equals minus 10. Okay, so we can go back and forth between the augmented matrix representation and the system of linear equations that you're probably a little bit more used to seeing. Okay. We just did a prolonged example of showing what you're allowed to do without changing a system of linear equations. And we're going to start to call those things elementary row operations. Okay, we just did this. We showed A, B, and C do not change the solution set of a system of linear equations. We multiplied one of the equations by a non-zero scalar. We interchanged two equations, and we added a multiple of one to the other. Now what I've got here is simply, this is with 4 equations. So you can imagine doing this operation on your equations and then seeing what happens to your augmented matrix. Well, I mean, this is what happens. If you do that one, it's the same as multiplying a row of your augmented matrix by a non-zero scalar. If you do this one, interchange two equations, that is the same as interchanging two rows in your augmented matrix. If you add a multiple of one equation to the other, that is exactly the same as adding a multiple of one row to the other in your augmented equation. So these rules are the same. The first set of rules, A, B, and C, are when we're thinking in terms of the equations. And the second set of rules right here, A, B, and C, are when we're thinking in terms of the augmented matrix. I'm saying exactly the same thing though. Okay, so we'll just take a final example, and I'm going to go through this in sort of what I would call kind of goryish detail to show how we can take a system of linear equations. In this case, it's a fairly simple system. We've got two equations and two unknowns. We can write the augmented matrix. We can sort of simplify the augmented matrix using these row operations, these elementary row operations that are these things here. These are the elementary row operations, and we can then observe that we can see the solution as we're going. So let's start out here. I'm going to do things both ways, sort of trying to show how these are equivalent. I know you can already solve this 2x2 system, but let's see how we can do it this way. Here we got the augmented matrix. There it is. So that is the augmented matrix corresponding to those two equations. And then what I'm going to do is I am going to multiply the second row by 2. So I'm gonna make a little symbol like this, and what I'm doing now is I'm taking R2 and I'm replacing it with 2R2. So I'm multiplying the second row by 2. I'm taking R2 and replacing it with 2R2. I'm going to write that out right here. That's going to look like this: 2 minus 3, 1. I didn't do anything to row 1. And to row 2, I'm going to multiply all the numbers in row 2 by 2. 6. Okay, what does this look like? Well, let us write what the system of equations is for this. That is going to look like this: 2x minus 3y is equal to 1, and 2x minus 2y is equal to 6. So you can see that this system of equations here corresponds to this matrix here. Okay, and you can see that what I've done going from here to here is multiplying by 2, and going from here to here is multiplying by 2. Okay, am I making any headway in solving this thing? Let's see. I'm going to keep it in black here. Okay, let's see what's happening. Now what am I going to do? I'm going to take this augmented matrix here. I'm going to make a little tilde here. I'm going to do something. I'm going to take R2, and R2 is going to be actually R2 minus R1. I'm going to take R2, I'm going to subtract R1, and I'm going to put that back into R2. I get here. So I'm not changing R1. And I take R2 minus R1. So I take 2 minus 2, 0. I take minus 2 minus 3, and I get 1. And I take 6 minus 1, and I get 5. Okay, let me write out what this system is. This system looks like this. 2x minus 3y is equal to 1, and y is equal to 5. That is the same. I could do the same thing here. I could just take this equation here, this one, and then subtract that one, right? So I would take here, if this was 2 and this was 1, I would go 2 minus 1, and I'd be with those two equations there. Okay. Now I'm going to do something else. I'm going to take R1, and I'm going to replace that with R1 plus 3R2. Okay, I'm leaving R2 alone. Let me just write that in. And I'm going to take R1 and I'm going to add 3 times R2. Okay, let me write out the equations. 2x equals 16, y equals 5. Okay. So again, looking at these equations, if I now relabel this 2 and this 1 here, and I was what am I doing going from here to here? I am taking 1 and I am subtracting 3 times 2. So go through this example very carefully yourself. Make sure that you can manipulate the equations, and then you see how the equivalent manipulations are happening in the matrix, because that's key to understanding what we're going to do. We're going to be doing this over and over and over again. We will definitely have a lot of practice with this. Okay, I'm going to do one final thing here. I'm going to go here. I'm going to say, listen, I'm going to take R1 and I'm going to replace it with a half R1. Okay, this is multiplying a row by a non-zero scalar. 1, 0, 8, 0, 1, 5. Now I write out what this augmented matrix is when I write it out as equations, and it looks like this. X equals 8, y equals 5. And folks, that is very exciting. We have a solution, right? There's nothing else to do. So we now have a solution. Now I'm going to write out the equations that we started with in the beginning right here. Okay, and I've gone through this procedure, and I have done these elementary row operations, and I've come to a place where when I write out what this is telling me, I basically have a solution. X equals 8 and y equals 5, and I could write that like this if I liked. Okay, let's see if that works. Okay, X is supposed to be 8 and y is supposed to be 5. does that equal 1? Well, let's see. It equals 16 minus 15, and that equals 1. Yes, nice job. Okay, x is 8, y is 5, and I subtract that, I get 3. Does that equal 3? Yes, it does. Okay, so I have, in fact, solved this 2 by 2 system, and I've gone through doing it with the augmented matrix. Normally when I would do this, I would not be writing all of these sort of translations by the side. This is for us to see what's going on the first time this comes up. Normally that will not take up this much space with this much writing. And this is just to make that clear. Okay, so that is our introduction to systems of linear equations. We'll be back with a rigorous and methodical way of taking any augmented matrix and seeing if we can figure out what the solution set to the underlying linear equations are in the next lecture. Thank you. Bye.